Hello, everyone. First of all, I would like to thank the organizers of this meeting to invite me. I'm very happy to be here and have the opportunity to tell you about our recent work on what you can read there, the control of ultrafast molecular photodissociation in conditions where a laser field is strong enough to change the situation. Okay, we've heard all the talks this morning about ultra-short pulses, some ultra-short laser pulses, light pulses, and of course ultra-short electron pulses. I'll stick to the laser pulses. We know that they are excellent fast cameras with which we can see rapid changes in matter. And of course this lies at the core of the field of femtochemistry, which was founded by Professor Zeeweil, whom we have seen this morning. Most femtochemistry experiments are based on pump probe schemes where a laser pulse, a short pulse, initiates a process, a dynamical process, and then a second pulse is used to monitor the changes that the system has suffered in a given period of time. The talk I'm going to give will add another ingredient which has been around for some time. This is the control ingredient. I'm not too fond of the term control, but what I mean by it is we will look at how process in molecules happen in the presence of light, of strong light fields. Why do electric fields of the laser modify this? Well, because if the laser is sufficiently intense, then the electric fields that the atoms and molecules see, the fields that the charged particles in matter see, can become comparable to the internal natural fields. And of course, that changes the landscape, let's say. So in the experiments, I will basically tell you about two experiments and the theory that has helped us understand them. The laser will play three roles. One is the initiator of a reaction, of course the detector of the reaction, as in traditional femtochemistry experiments, but also I use the word sculpture, because we will use lasers that are intense enough to distort the landscape. So this is the outline of my talk. I wanted to very, very briefly review some of the schemes that have been used to change, to modify chemical reactions. Then I will describe the process that I want to modify, and then I will tell you some of the results. So let's start with the schemes. Of course, one would say, well, if I want chemical selectivity in a fragmentation of a molecule, I want a particular bond to be broken and not other bonds. This is difficult to do with a laser, particularly if one thinks of hitting a vibrational motion, because motions are interrelated. Vibrational energy redistribution occurs very fast. And although some examples do work, especially using UV excitation, but this in general is a scheme that does not work to achieve chemical selectivity in a process like photodissociation, for instance. I wanted to mention the fact that we use ultra-short laser pulses puts us in a privileged situation, because we are not longer limited to exciting one particular state, as we do with a continuous wave CW laser, as the graph shows. With ultra-short laser pulses, we excite several components, several vibrational components in a coherent way. And this gives us a lot of freedom, because we can use combinations of pulses, sequences of pulses, to guide these wave packet to the places in the parameter space where we want them. So tailored light, if we can modify the properties of light, then we can guide wave packets. And this is all without actually changing the potential energy surfaces, just guiding these wave packets to move at the time where we want them to. So in general, the molecules are complicated, so people have used sophisticated pulse shames in time and spectrum to achieve control, and typically without knowing the Hamiltonian, what's behind And these are usually termed closed loop control of molecular dynamics, or the idea of teaching lasers to control molecules since we don't know, right? So these schemes work in a loop because we have devices that can modify the properties of the light in such a fine way, so with so many parameters, that we can try the experiment, see if it works, and then come back and try another design of a laser pulse. And these schemes have achieved a lot of success. I will now move into the strong field regime, where by strong I will mean moderately strong, laser fields that are strong enough to modify, but not to produce a high degree of ionization. Professor Moshammer this morning made my life slightly easier, because he mentioned a lot of the concepts that I will be needing, like the address states. If you look at that picture there, the way we normally look at a transition is we think of it as a transition between two states. But as the fields become strong, it's useful to move to address state picture, to remove the photon, and imagine that new states appear that are shifted by the amount of a photon, or of one photon energy. So of course, in this situation, new crossings appear. And some years ago, people like Zirbam and Moseyev used the new term light-induced or laser-induced conical intersection to term these new crossings between states. Of course, this is related to processes like bond softening or bond hardening, making bonds that stay together for a longer time because a laser field is present. So now that we've seen like the background for the work that I will be describing, I will tell you about this ultra-fast dissociation process, the one I'm interested on. And this is how the bond carbon-iodine breaks in a pretty simple molecule, but instead it's a polyatomic. This is methyl iodide. So this is the situation. In the UV, methyl iodide absorbs light efficiently, and there is a whole set of repulsive states, although the dipole is mainly concentrated in one state. And from there, dissociation proceeds very rapidly. The CI length distance increases rapidly. There is also a crossing, and so two possible outcomes of the process are possible. One of them leads to the iodine atom in its spin orbit excited state, and the other to iodine atom in its ground state. And this is because of a natural crossing, a natural conical intersection. So the way we look at this molecular photodissociation process is relatively simple. We have our TISAF laser. We split it in two, and we use one of the arms in the UV to break this bond, and the second arm, and this is a traditional femtochemistry, to remove an electron from one of the fragments that appear. Then we look at the image of charged particles, like that. Oops, sorry. And these images of fast particles, these are velocity map images where we know the speed distribution and the angular distribution of a certain particle that we're interested in. For example, here I'm looking at the images of the methyl fragment. And as I was telling you, we have two channels, and these correspond to the main two rings that you see here. So we can see this process, and we can see it happening. We can see it happening in time, and this way we know how fast this process takes. It's an anisotropic because it takes less than a rotational period. We see both channels, and it's a relatively fast process. So what we set out to do is, okay, we want to look at this process, which we understand quite well. We've published a series of papers on it, and we want to know how it happens when there's a laser field there. So, okay, what can we expect to control? Well, mainly it's the quantum yields, the kinetic energy releases, how fast do the fragments end up in this process, and also the angular distributions, although I will mainly focus in the first two quantities. So this is what we want to know. From the experimental side, it is conceptually simple. What we have to do is simple. We just have to add another arm that provides us this third laser in the system. So we stick to the ultraviolet excitation. We add this additional arm, and this will contain a strong or moderately strong infrared, near-infrared field. And of course, the detection laser, which is resonant with the transition of one of the fragments. So these are the kind of results that we obtained as we move this strong laser in time with respect to the pump. I have to add here that the first experiment that we did, we said, well, we want the laser field to be there all the time. So in order to have that, we stretched it. We introduced some chirp in this pulse. This means that the low frequencies come before high frequencies, and it's long in time. It's about 4 picoseconds in time. For the time scales of this process, it's always there. So these are the situations that we have. When it precedes the pump pulse, then our image looks just like the images that you saw before. But when there is some degree of overlap with the pump, the situation changes in one aspect. We get an additional channel that is redshifted. It has less energy than the well-known channels. Don't pay attention to that. In this case, there is some shift, and this is why we still see this additional channel. So if we plot these images, we forget about the angle, and we just plot them as a function of speed. We see the known channels that I described before, and this new channel, and it has an additional feature, is chirped. Its energy changes as we move this long pulse along the pump. And I just want you to know the description we have of this new channel. Here is the initial absorption process. The control field, we can imagine that it produces a replica of the ground state, and now we have this light-induced conical intersection, a new crossing between the states, and part of the wave packet that was dissociating can leak through. This is very analogous to what Professor Moshammer was showing this morning, and of course part of it does dissociate on the ground state, producing this new channel. The fact that it's the fact that it's chirped reflects the fact that the frequencies of the control pulse change in time. And of course, this determines how far from the equilibrium distance this new crossing occurs. And this in turn determines the kinetic energy at the end. So this proves that we have created a light-induced conical intersection, the dissociation of the wave packet. And this, of course, changes the quantum yield, because part of the wave packet goes to the spin orbit ground state of the iodine fragment. Sorry, I seem to go further and back. Okay, I would like to tell you about the theory done by our collaborators, Jesus González Vázquez and Ignacio Solá. Jesus is in the audience, using this Floquet picture, already mentioned this morning too. So in these videos, you will see here the laser pulses that we have used. Here are the potentials and the wave packet in position space, and here you will see the wave packets in velocity space as the dissociation process proceeds. We will start with a trivial situation, no control field, just dissociation of methyl iodide after UV absorption in its first absorption band. You see that the pulse is there. You form the wave packet which dissociates in the excited state. It gains momentum here initially, and then this momentum is decreased because this excited state has a small well. So this is just the standard dissociation. Now I will go to the situation that is analogous to what I just mentioned in the experimental side. Hello? Okay, here we have a long and relatively intense control field. And this is the situation. We already have the shifted ground state, and we will have the lithi appearing. So as let's see. Okay, no. Oops. Okay, let's see. No. Well, doesn't seem to be working. Never mind. Okay, never mind. I will describe it if it's possible. Yeah. Okay. So, well, the video doesn't work, but believe me, what happens here? What happens here is that we form this initial wave packet in the excited state, and at some point, when we reach the crossing, then we see a second wave packet evolving in the ground state of the molecule. And of course, we obtain then at the end of the process, we obtain 2 peaks in velocity space, and these are the 2 asymptotic peaks that we get in this plot. Let's see if the following one works. Otherwise, I'll go to my computer. Hello. I'll go to my computer. Oh, we're here. Okay. Yes, okay. Right. Okay, so this is what happens. We don't have an analogous for this in the experiment because we never used long and such intense laser pulses. But here we have the intensity of the laser pulses is that strong, is so strong that basically dynamics occurs on the lips. And therefore, well, it's too late now, the wave packet has transferred already. We get a complete transfer of population from the excited to the ground state. It is remarkable that we do see that dissociation occurs entirely on the lip, and therefore transfer is complete. As I was saying, the control here is exerted by the laser intensity. The theory group also did some simulations in 2D to try and see if they could obtain something that was analogous to the experimental result, and they did. They observed this new channel with the same kind of chirp. So here we see that in this situation of long and moderately strong laser fields of around 10 to the 12 watt per centimeter square, mainly is the chirp and the intensity, and of course the delay, which determines what kind of control is possible. We will now go into a situation where we have a much shorter control pulse because we want to add another ingredient. We want to introduce this pulse at controlled moments of time when the wave packet is dissociating. So we will do this experiment with a 50 femtosecond near-infrared pulse. And I will just go straight to the result that we get in the form of a map that is analogous to the one you just saw. This is the main channel of the process, the one that yields iodine in its spin orbit excited state. We still see this channel. And in the time that we have some overlap, we see this in the new channel, the lithium channel is there too. And we see something else. We see a distortion in the main pathway, a shift to the red and a broadening. So again, the situation is in a way analogous with the introduction of strong laser-induced potential. Let's say if the intensity of the laser pulse is sufficient, then we have to consider that we not only have dress states, but we switch from field-free to dress states, and this causes new phenomena. The theoretical description of there appears on this plot. We have chosen here a short and strong control pulse at a delay where the wave packet is exactly going through the conical intersection. This causes switches, as I was saying, and has the power to act as a momentum filter. Why is that? Because dissociation is first proceeding naturally, But the fast components of this dissociating wave packet reach the crossing position before the control pulse has a high intensity, whereas the slower components of the wave packet are later and suffer the presence of the laser-dressed potentials. And of course, this makes the pulse sequence, the moment of introduction of the short and intense pulse, a new tool that can select the momentum components that end up in one channel or the other. Let's see if this works this time. This is the situation in this case, applying this short pulse at 60 femtoseconds. We'll try again. Okay. So as you can see, we have the wave packet in the excited state. Then we apply this second intense and pulse with a rapidly changing intensity, and this produces the redshift, the new channel, and the broadening. And what is important here is that adiabaticity is broken here, and this is why the wave packet may appear on the other lip. Of course, as the wave packet is dissociating, at the point in time where the laser is at maximum, it sees the dress potentials, and this introduces a more attractive potential, and this shifts its momentum to the red. So we have shown that we can control this. The simulation, you can see the simulation there. All the main features are reproduced in the 2D simulation, the new channel and the broadening and the shift to the red, although to a lesser extent, but they are there. And this is the summary of the experiments and the theory. As I was describing, this represents the trivial situation, no control field. This represents the situation where a long, moderately intense field causes a laser-induced conical intersection, and then we have a leak of part of the wave packet, and this produces a chirped contribution. This is the next step in intensity while keeping the temporal properties the same, and in this case we observe that we can have dynamics in the laser-induced potentials with no experimental counterpart. And lastly, this situation, the most interesting situation, where we can play with the field-free versus the laser-dressed states, obtaining new effects in the channels and in the kinetic energy distributions. This summarizes what we have observed in these and other systems. We have also been able to control lifetimes, for instance, or angular distributions that I haven't described, but we have published recently. These experiments have been done in the Centro de Láseres Ultrarrápidos, ultra-fast laser center in the Complutense University in Madrid. These are the people who have been involved in all the work. Luis Mañares, who is the head of the group, Gary Cois Valerdi and Maria Eugenia Corrales, the PhD students, and of course the theory people whom I have introduced before. We have recently published a perspective article in PCCP. And with that, I just have to thank you for your attention.